Okay, so let's implement the quicksort algorithm using the implementation we went through on the slides. We're going to code two methods, one called quicksort and one called partition. So let's start with the quicksort method first. So we'll say public static void quicksort, and we're going to pass the array we want to sort, the start index, and the end index. And as we saw on the slides, the end index will be one greater than the last valid index in the array. So the first thing we're going to do is check whether end minus start is less than 2. Because if end minus start is less than 2, we're dealing with a one element array, so we don't have to do anything, we just return. If we're dealing with more than one element, then what we want to do is figure out where the pivot will belong in the sorted array. In other words, what will be the index of the pivot when the array is sorted? What is its sorted position? And so we're going to say int pivot index equals, and we're going to partition this array. And we'll write the partition method in a minute. So what this will return is the position of the element in the sorted array, so its correct sorted position. So in the slides, we had 20 as the pivot, and eventually the pivot ended up in position 4. And so what this would return is 4. So it's basically returning the position of the pivot, and at that position, everything to the left of the pivot will be smaller than the pivot, and everything to the right will be larger. And after that, we want to do the same thing with the left array and the right array. So all the elements that are smaller than the pivot and all the elements that are larger than the pivot. So we're going to call quicksort with start as the start index and the pivot index as the end. And then we're going to call quicksort with the same input array, pivot index plus 1 as the start index and end as the end index. What we're saying here is, in this step, we have put the pivot into its correct sorted position, and we have repositioned the elements such as everything to the left of the pivot is smaller than the pivot and everything to the right of the pivot is greater than the pivot. And then we want to do this quicksort the left subarray, and we want to quicksort the right subarray. And once we've done that, the entire array will be sorted. Now, of course, these are recursive calls, and so what actually happens is when we call this quicksort, it will deal with the left subarray, but then it's going to make a recursive call to then deal with the left array of that subarray, etc., until it's completely handled the left subarray. And then, and only then, will we start working on the right subarray. So keep in mind what happens with recursion, and if you need to, go back and review the video on recursive methods. Okay, so let's write the partition method. So we'll say public static int. This is going to return the correct position of the pivot in the sorted array. Partition, we're going to accept an input array, a start index, and an end index. So I'm going to put a note here that says this is using the first element as the pivot, as we saw in the slides. So we're going to start out by saying that the pivot is equal to input start. Now, of course, this is the start element in the array or subarray that we're passing. So it's not necessarily index 0. Later on in our example, we had put 20 here as the first pivot index, and so the right subarray would be starting at index 5. And so that 1 would actually be the pivot when we call partition with this right subarray. And then, as we did in the slides, we're going to set I to start, and we're going to set J to end. And now we're going to do the traversals. Remember that I is going to traverse from left to right, and J is going to be traversing from right to left. And we want to stop when I and J cross each other. So we're going to say while I less than J, because if I is greater than J, it means they have crossed. Okay, so what we're going to do in here is we're first going to use J to look for elements that are less than the pivot. So we're going to say while I is less than J, because we want to stop if I and J cross. So if J crosses I, we want to stop. And while input minus minus j is greater than equal to the pivot. That's all we want to do. This is an empty loop. I'm going to put a note here to say note empty loop body. And so we're not doing anything within the body of the loop. So we're just basically using the loop to keep decrementing j until we either find an element that's less than the pivot or j crosses I. So what do we do when we fall out of this loop then? Well, we've got to make sure we didn't fall out of it because j crossed I. So if j hasn't crossed I, if I is still less than j, then we want to move the element at j into position I, because basically we have found the first element that is less than the pivot, and so we want to move that towards the front of the array. And so we're going to say input I equals input j. And if you're confused about this, go back and review the last video with the slides. But essentially, we're saying we've used j to find the first element that is less than the pivot. And we want to put all the elements that are less than the pivot to the left of the pivot. And so we're going to move that element at j, the one that we found that's smaller than the pivot. We're going to move it to position I. And on the first iteration, I is actually at 0. So if you'll remember the slides, the first pivot value is 20, and we're moving backwards, and we found minus 22, and we moved minus 22 into position 0. Okay, so now we want to alternate and go to I, and we want to traverse the array from left to right looking for the first element that's greater than the pivot. So we're going to say while I is less than j, because once again we want to stop if I crosses j, and input plus plus I is less than or equal to the pivot. And once again, this is an empty loop. And I'll put a note there because it's easy to miss. And so this time we're going to be moving from left to right, and we're looking for a value that's greater than the pivot, because when we find a value that's greater than the pivot, we want to move it to the right of the pivot. And so once again, we're going to check when we drop out of the loop whether we've dropped out because I has crossed j, and if that's not the case, then we've dropped out because we found an element that's greater than the pivot, and so we want to move it to position j. Input j equals input I. And it's okay to do that. We're not going to be losing any data because in the previous loop, we've already moved what was at input j. And so at this point, it's safe to assign to input I. And in the next iteration of this loop, it's safe to overwrite input I because we've already moved it. So it's the fact that we're alternating between I and j and which direction we're traversing in that lets us do these types of assignments without losing any data. Now, one important thing to note here, we're using the prefix decrement and the prefix increment operator. So what this means is when we execute this statement, we'll decrement j and then we'll use the result as the index. And recall that end will always be 1 greater than the last index of the array. And so if we didn't decrement, we'd get an index out of bounds exception if we'd pass the entire array in, or we'd actually be indexing one element past the end of the subarray that we want to work with. And it's the same thing here. When we first come in, I is start, I is the pivot. We want to start with the first element after the pivot. And so we're always going to be, we want to increment first and then use the index. And then on subsequent iterations, we'll want to increment first because we've already handled what's at I. So whenever we enter this loop, we've already handled the element at I, and so we want to increment and then use the index. We don't want to use I, or we're going to be looking at something we've already handled, and that's not going to work. Okay, so when we drop out of this loop, I has crossed j, and that means that we finished moving elements that are smaller than the pivot to the left subarray and elements that are larger than the pivot to the right subarray. And so at this point, the value of j will be the index where we want to insert the pivot. And so that's all we have left to do. And so we'll say input j, not I, equals the pivot, and then we have to return j, because remember what we're returning from this method is the index where we inserted the pivot, because that's how we're dividing the array, and we need that to then call quicksort for the left array and quicksort for the right array. And you'll notice that when we call quicksort for the left array, we pass the pivot index because, as I said, the end index is always going to be 1 greater than the last valid index in the partition, in the array, the subarray that we want to partition next. And so we really, for the left subarray, will go from index start to index pivot index -1. And so we pass pivot index because we want to pass one greater than the last index we're interested in. And that's it. That's our quicksort algorithm. Keep in mind that this is recursive. So when we come in here and we call quicksort on the first left subarray, this is not going to return until the first left subarray, this subarray here, because remember the first pivot element is 20 and we end up inserting it here. So the first left subarray that we're going to call this with is this subarray here. This quicksort call is not going to return until this entire thing has been quicksorted. And so by the time this call returns, all of this will be sorted. And the same thing goes for this quicksort. By the time it returns, this whole subarray will have been sorted. So let's run this to make sure it actually works. And of course it doesn't work because I haven't actually called quicksort. So we're getting here the unsorted array. So we're going to call quicksort. We're going to pass our int array. We're going to pass 0 for start. And we're going to pass, that should be int array, 0 for start and int array.length as the end index. So let's give this another shot. And now we have our sorted array. It always helps when you actually call the sort method. So -22, -15, 1, 7, 20, 35, and 55. So if you're having trouble understanding what's going on here, go back to the slides. And the key point to remember is that we're alternating between I and J. We're alternating between traversing from right to left, looking for smaller elements, and going from left to right, looking for larger elements. And because we're alternating, we can do all of this in place without losing any data. And if you're having trouble understanding the recursive nature of it, go back and review the video on recursion. So that's it for quicksort. That's the second divide and conquer algorithm we've seen, but we're not out of sort algorithms yet. So I'll see you in the next video.